Welcome to the Cosmic Pie Podcast, Episode 9, Season 4. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
We are broadcasting live from the campus of the University of North Dakota here in Grand Forks, North Dakota. We have a chat feature that is running, so if you have any comments or questions that you'd like to ask us throughout the podcast, feel free to use that. And before we get going, I also want to state that if you like this podcast, please remember to give us a what, Robert?
Thumbs up and a like. Subscribe if you want to. Hopefully you'll want to.
But don't hit it twice. You know, if you hit it twice, what happens?
It unlikes.
It unlikes.
Yeah.
So you can like and unlike.
Yep. And then like again.
But you can't just unlike. Like, how do you... You see
Yeah,
what I'm
you
saying?
can give it a thumbs down.
Oh, you can?
Yeah.
I only see a thumbs up if you hit it.
Nope, there's a thumbs. Should be a thumbs
Oh,
down.
yeah, there is a thumbs down. I never look at that. I'm not that cruel to want to give someone a thumbs down.
And if you go in and look at the analytics, it'll show you your thumbs up versus your thumbs down.
But so far, I don't think we've had any thumbs down.
Excellent.
This might be the first one. Hopefully
This might
not.
be the first one.
Hopefully not. Now, as a disclaimer, Robert, since you are feeling a lot better this week.
I'm feeling a lot better. As you can tell, I'm still coughing and everything, but I'm still feeling better. So, the opinions and views expressed hereon are those of myself and Wayne. They are not the views of the Department of, who do we work for again? Oh, yeah, the Department of Physics and Astrophysics, the College of Arts and Sciences, the University of North Dakota, the state of North Dakota, the United States of America, the world at large, the solar system at large. You get the idea. It's just us, folks.
Yes, we're the only ones to blame or
praise.
or praise.
Praise.
Yeah, please. After you give us that thumbs up.
Yeah,
And
we're
don't
being
forget,
a little silly today.
don't forget
folks.
to subscribe.
Yes.
Why are we being silly today, Robert? What's happening next week, Robert?
Oh, next week is spring break.
Spring break, and we will be here. One of us will be here.
One of us will be here. Wayne will be here. Or at least he will be trying.
I'll be trying to be here. Now it'll look a little different.
It will.
Because I'm setting up all of the software that we use to stream live, namely OBS for those who are curious. I'm going to run that from my own laptop in my office upstairs. And I'm going to see how that goes. And that way, if there's any time when you're not feeling well and you can't make it, or you're traveling, like the case during spring break, that I can, sort of run things myself. Robert is our de facto producer. That's why
That's probably why you should blame me, not even Wayne, when things don't go quite right. Because, yeah, it's me trying to figure this stuff out, folks.
And that's why he makes the big bucks.
I do?
Okay, I imagine that part. Sorry.
Okay.
That's what you call daydreaming, you see.
Oh, all right.
That's
now
why
we hit the 1 million subscriber mark, and there'll probably be some big bucks involved, because at that point I would be talking with the university and the state and saying, "Hey, we're bringing in money now."
Robert, there was some monopoly money around here somewhere. I can give you that if you like.
Fair.
Just don't buy Park Avenue. I like that one.
Okay.
Okay.
I'll get Boardwalk.
Now, the other thing is we always upload our podcast on Spotify the very next day. So if you're rather listening to it on that media, you can feel free to do that.
Absolutely.
Now, Robert, you want to tell people why you're not going to be here next week and why you're going to be traveling, why you're leaving me behind, why I'm going to be stuck here and not be able to venture off somewhere on spring break. And don't tell me you're going to Tahiti, Robert.
No,
please. I will cry in front of everyone.
I am not going any place that's much warmer or anything like that. But as I think we've mentioned on the show before, I have recently published and authored a book.
Yay!
So I did ask first, hey, would you like me to come as a guest author? And they said yes. And there's a small fan convention in Cleveland, Ohio. And I am going to be a guest author at this fan convention. And it is called Cleveland Concoction.
You're famous, Robert.
Yeah, if you're in the area, feel free to drop by and say hi. This is where they are. It's a small convention, so the prices are really relatively cool as far as getting in for your day. Like I said, come by, say hi. The book in question is this one right here. I've written, it's titled Mortal.exe. It's an old play off of the old DOS prompts, and the .exe file is an executable. So someone in my story is trying to run a executable called Mortal. It's a goddess wanting to be immortal.
Now, don't spoil it.
And that's as much as I'm going to say.
Okay. And where can you find this lovely book?
It is currently on Amazon as either an ebook or you can get the paperback version. So
And it's not too expensive.
it's not terribly expensive. I tried to keep it in play. I didn't want to shortchange myself, so I'm sorry. Yes, it's $16. But at the same time, I don't want to kill everybody. A lot of people are doing $20, $25 for their books. I want you to read my book, and I want you to have fun with me. So,
And as an author, if you look at the total amount of money that you accumulate by selling your book, it comes out to be like a penny an hour or something like
something
that.
like that. Other friends.
You don't do it for money.
Oh no, other friends in one of my writing groups. I belong to two. Often calls this her expensive hobby. Because, when you run about $500 or much more, up to much more, to do your editor, another $100 to do your cover, it all adds up. And the next thing you know, yeah, you've put $1,000 into it, and then you put it out there. And let's face it, even when you're with the big 5 publishing companies, most books sell under 1,000 copies.
Wow.
These days. So I encourage you to write. I encourage you to publish. Do not ever get me that wrong, okay? But if you expect to be a Stephen King, Clive Cussler, I believe his name is, somebody like that, set your expectations a bit lower.
You remind me of podcasters.
Right.
You can make money podcasting. We don't. We're not monetized. We don't
Right.
want to be monetized. Obviously, we do it as part of the University of North Dakota. But for those out there who are monetized and trying to make money, there's only a selected few that make it. And when they make it big.
They do.
You
They
think of
blow
like
up.
Joe Rogan and other people, right?
Yeah.
They must make a lot of money per year off their podcasts.
Yeah. So, I don't want to discourage anybody.
Yeah.
But go into this with your eyes open. I do it because I like telling stories.
Right. Well, talking about
Telling stories.
telling stories, let's go to our first astronomical slide. I don't know if any of you had good weather in the morning, but there was a total lunar eclipse. That's when the moon goes into the shadow of the Earth. And for us here in North Dakota, that totality started roughly at about 5 a.m. and went to about 6 a.m.
Okay.
Now, Robert, you know what I did this morning? I got up.
You got up. You actually got up?
I didn't wait till
Wow.
noon. I actually got up in the morning.
Okay.
And when I got up, and I was around 4 o'clock, guess what it was doing outside? And we're
Snowing.
landlocked, right?
Right.
No, it wasn't snowing, but
Fog?
it was fog, ground
Okay.
fog like crazy. So much so you couldn't see the full moon.
Holy cow.
Yeah, it was that thick. And then I
Wow.
checked again at 5 o'clock, the beginning totality, same kind of thing. The fog had lifted, but it was still extremely cloudy. Right? The fog moved above us rather than
And then about 6:30, the sun was starting to
well,
light up the sky.
5:30 I got up and looked out as well. That was in the middle of the
Okay.
total totality. And what I did notice, of course, it was a lot darker than it had been an hour or so before that. So definitely you could tell that the full moon was covered up by the shadow of the Earth at that point. But once again, it was too cloudy. I couldn't see it.
Yeah.
And then at that point, I went back to bed at 5:30 and said, okay, there's no point getting up until I have to get up to go to work type of thing.
Yeah.
So hopefully those of you who are listening from afar or do listen to this eventually from afar, you had better luck than we did here in Grand Forks. So,
Yeah.
And the next total lunar eclipse will take place on New Year's Eve in 2028.
Oh.
So a little less than 3 years. So you got to wait a while for the next one.
Yeah.
So it's like, darn, I wish this would have. I had everything ready. My
Well-
camera on the tripod, all of that stuff was ready to go.
And
But it's
this
the
one
weather.
for us here in North Dakota, though, it wasn't actually a full eclipse, was it?
Yeah, it was totality.
It was total.
Yeah.
Okay. I
Yeah.
thought it was just partial because I know the center of totality was out in the middle of the Pacific.
No, it was for us. We could see it all just when
Okay.
the moon was setting. So we were okay at
Okay.
this spot. If you're out in the East Coast, of course, that was definitely the case.
Yeah.
You'd only see
And-
part of
and
the eclipse.
I heard from my Georgia friends that they were clouded out completely and things like this. So
Oh, well. I mean, they were at the mercy of the clouds, at the weather when you do anything related to astronomy when you're on the ground, obviously.
and no offense, but as you were just pointing out, another one in 3 years.
Yeah, just got to be.
Lunar eclipse.
That's the reason to eat healthy.
Yeah.
Whole
Stick
food,
around.
plant-based diet, Robert. That's the way to go. You want to live to be 150.
I really don't. Not unless I'm uploaded into a machine body and.
I'm not going to say you won't be in a wheelchair by then, but anyways, it's the quality of life that matters too, right?
As exactly, So.
Anyways, now major. Can I say that one more time? Major shakeup at NASA in terms of the Artemis project. So a little bit of an update first for everybody. So all of us have been waiting around for Artemis 2 to take off with astronauts for the first time on this space launch system. The goal is to whip around the moon and come back to Earth to test a lot of the equipment, like the environmental system. Believe it or not, they need to check or test the heat shield. So if you were with us last week on the podcast where we had Dr. Space on from the space show, he went into a lot of detail about the Artemis project, about human exploration of space and what has happened in the past, what's going to happen hopefully in the future. And since that podcast, NASA made a big announcement last week that they are changing, if you like, all of the Artemis project essentially. Artemis 2 will be the same. I mean, that's so close to being launched, why change it? Now, the rocket had gone through the wet dress rehearsal for the second time and had passed everything. So all the hydrogen leaks that they had were all fixed. Everything looked really good to have a launch in March, what everybody was hoping. A lot of people are down in Florida on spring break in March. It sounds like a real good opportunity to catch the launch. But one of the things they tried to do was to have helium flow into the upper stage of the rocket. This was after the wet dress rehearsal, about a couple days later or so. And they found out that the flow rate was too low. They couldn't do what they expected. Now, something is blocking the flow of the helium. Maybe it's a filter or some other situation. The problem was because it was up in the upper stage, it wasn't designed to be, if you like, fixed or maintained or repaired by humans when it's on the launch pad. They didn't have access to it.
So that's why they're having to dress it down.
So they had to then take it and roll it back to the vehicle assembly building, which happened several days ago. So it's being fixed now. I haven't heard the update, the latest, greatest thing of what's going on, what caused the flow issue, but hopefully that'll get fixed. And then they got to roll it back out to the launch pad again.
At like, what, a meter an hour?
Yeah, it's very slow. It's like roughly 10 to 12 hours to get a few miles.
Yeah.
And the thing is, there's no way to make the March launch, and you don't want to rush so much that you're causing a potential safety problem.
Right. I mean, if it were going up unmanned, rush it a little bit, you lose the vehicle. You got people going to be on the top of it this time.
And losing the vehicle, I mean, this thing is worth several $1 billion.
I agree, but
it's expensive, like $4 billion or so, depending on who you listen to, who the accountant is. But the next opportunity to launch, as you see there in the bottom of the slide, is in April. So this includes April 1st, and then between April 3rd and April 6th. So once again, if you're down at the Kennedy Space Center, you may have a chance to see the launch. Hopefully no other problems crop up in the meantime, and they're able to make one of these launch opportunities in April. We will see. And of course, you're at the mercy, obviously, of the weather.
So
the weather has to be
April isn't
right.
exactly noted for being the prettiest time of year.
Yeah,
in
so
Florida.
things could be delayed because of that. But the major shakeup that happened with the Artemis project is not related to Artemis 2. It's related to the future Artemis launches, starting with Artemis 3. So if you see in the slide, if you go at the very top, 2026, so that's, if you like, showing you what's going to happen with Artemis 2. As I said, it's designed to go to the moon in about 4 days, to whip around the moon and come back, 4 days to come back, roughly, altogether taking about 10 days, the total mission time.
Okay.
And Artemis 3 was to be the first landing on the moon, and that is not going to be the first landing on the moon. Artemis 3 now, and it was scheduled, by the way, I mean, these schedules keep changing around. The important year in all of this happens to be the year 2030, and the reason why 2030 is important is because China has announced that they want to send humans to the moon, and their time frame is about 2030. So the idea is the United States wanted to beat China back to the moon.
Yeah, we beat the Ruskies, now we got to beat China.
Beat the Russians, the Soviet Union back in the 60s. Now we're going to beat China here in the year 2020s. And so they wanted to land on the moon before 2030. And the problem in all of this is that the lunar lander, the one that gets you from lunar orbit to the surface, is not available. It's not ready to fly. And there are two companies that have been given contracts to develop the lander. One is SpaceX, the other one is Blue Origin. And SpaceX has been promoting the Starship, which they've launched several times now. And that's the one that goes sort of suborbital flight and then lands in the Indian Ocean. And they're trying to progress, if you like, the technology to the point where they can use that to go from lunar orbit down to the surface of the moon and then launch again from the surface of the moon when they're ready to return. But the technology is not quite there yet, and we don't know when it'll be available. But Blue Origin is also trying to develop a lander to do the same kind of thing. It's not the same as the Starship. It's more, I compared to more like the lunar module from the 60s than Starship from now.
Now, they are still planning on actually launching it on the Glenn rocket, right?
Yeah, that's still the idea, is to do that. But the first is to provide a lunar landing to NASA to be used for the Artemis project. And
sorry, but that disturbs me a little bit, too, that the humans will be launched on the SLS, but then the lander will be either on a Starship or a Glenn rocket. And they'll have to meet up there?
No, the lander will be inside the Artemis, inside the SLS rocket.
Okay. Right? I thought they were going to launch.
For the Blue Origin.
Oh, okay.
Right? Because it's a different design that's going to fit inside. And so all of this is like, and this is subject to change, right?
Absolutely.
Put a big asterisk on all of this stuff. And that's the problem. It's not well laid out, the plans. And it's like, well, if we develop this in time, we're going to do that. And the Starship developed, we'll just launch that on our own, and we can, okay, let's see what happens, right?
Right.
And the pressure of the schedule is to get there before 2030 to beat China. Now, China takes 2031 to get there, 2035 to get there, then that gives the United States more time to develop out the technology to get there and not have to push it. There is some political pressure. If you listen to the NASA administrator, Jared Isaacman, last week, you can tell there's political pressure. And the schedule has been changed such that now Artemis 3 is actually going to just go into Earth orbit and test the lander.
Okay.
Right? And then Artemis 4 and 5, one of them would be the one to be the first soft landing on the moon.
Why not test the lander by actually just doing another slingshot around the moon? As you're approaching, deploy it, let it drop down a little bit halfway like we did with one of the Apollo missions, pull it back up, redock, swing back around the moon, finish the swing around the moon, and come back.
Okay, so let's do a little bit of a history lesson here about the Apollo program. So in the Apollo program, they came to a point where the lander was behind schedule for development. Sounds familiar. Same thing we're running into now.
Yeah.
It wasn't available. And so NASA was wondering what to do with the launches, the launch schedules. And what was decided was there was, I guess, information provided by the CIA that the Soviet Union was developing a large rocket that was on the launch pad, preparing it for a possible human launch to the moon. And so this would have beat the United States to the moon.
Yeah.
And sort of a decision that maybe they would have took more time to think about it than what they did. We don't have a lunar lander. What do we do? Well, we're going to take Apollo 8 and have it go around in orbit around the moon and then come back without the lander.
Right.
Okay? Because there's none available. But we're putting a stamp on our territory, if you like. Look what we can do with our technology. We can make it to the moon with humans, and we can go in orbit, around the moon and then bring them back. We can do all the necessary critical steps except just landing on the moon.
Except landing, right.
And therefore, we are far ahead in getting to the point where we can successfully land on the moon and return. And that showed the Soviet Union, it scared them into thinking how far the United States were in their development of their moon landing program. Now, it turned out that big moon rocket, as we know today, because a lot of stuff was kept secret, it failed, and the whole thing blew up. And it killed some people in the process. So it was a bad thing that happened. But what happened in the United States was that Apollo 9, which was, of course, happened after Apollo 8, after they returned from going around the moon in 1968, By the time Apollo 9 was launched, it went into Earth orbit because it had the lander, the lunar module.
Right.
So they put it through its test and low Earth orbit, so they're close to Earth in case of a problem. They can get back relatively fast, right? You don't want to be 4 days away on the moon and something happens to the lander, right? When you're just testing it for the first time in space.
Right.
You want to work those bugs out in low Earth orbit so you can get down fast if you had to for emergency. So that was successful, the Apollo 9. And what the next flight, Apollo 10, was to go all the way until you get to within like 50,000 feet of the lunar surface in the lunar module, and then come back.
Mm-hmm.
So you did everything except really the last 50,000 feet and land on the surface.
Yep.
And that then fell in the hands of Apollo 11, which was successful, as we all know. This was completely different. This was like, okay, you send astronauts up to check out the Orion spacecraft, the capsule, if you like, we want to call it that, and see if the environmental protection system all works so you can survive, you can live on the capsule for 10 days.
Mm-hmm.
And you go around the moon and come right back. And then the next one is just to go right there and land.
Right.
So what the NASA administrator said that that's too much of a leap, that we need to have at least one intermediate flight where we go up in low Earth orbit, check out the lander, like we did on Apollo 9, come back, and then we can go on Artemis 4 to soft land on the moon with the lander.
And my statement is I would think you'd combine Apollo 9 and 10, go onto the moon, test the lander by letting it drop, bring it back up, come back to Earth.
I guess the problem there, as I alluded to already, is when something goes wrong near the moon.
You're 4 days away. But
Yeah, so let's test out the lander very close to the Earth so we can get down in a few hours, right? Emergency splashdown. I think that's the idea.
Okay,
Right? Safety first, Robert. Safety first.
I'm just thinking that testing it in low Earth orbit, though, you're not testing a descent. You're just detaching it, blowing off a little distance, coming back.
Yeah, I mean, you can
reattaching.
fire the engines and all of that. You fire them in Earth orbit, right, as if you were descending. So they're going to put it through all its things, test out all the jets on board, so all the orientation things, the environmental control system that's on board the lander, they need to test all of that. There's a lot of things, a lot of engineering that has to be tested out. It's a new vehicle.
I'm not disagreeing. I'm just...
Yeah, and of course it's going to be tested in weightlessness, which it should. How does it operate? So you can't do it all from the ground, those sort of tests. Right. Those should be really done in space. I don't mind that. But then they're going to the moon. So what they're doing is eliminating Apollo 10.
Yes.
They're going from Apollo 9
to Apollo 11.
To Apollo 11. That's the idea. Unless something happens, and then they might have to use Artemis 4 to test the lander again because there were issues on Artemis 3 that the engineers needed to fix. Right? And then they tested again on Artemis 4 and then land on Artemis 5.
This is, again, why you plan it out instead of this...
Well, you never know what problems crop up, to be fair to the engineers.
Fair.
So you have to be a little bit flexible in that. And even NASA changed their schedule, right?
Okay.
The initial schedule for the Apollo program is not one that they followed at the end.
You're correct, yes. Because it was like 8 should have been the actual first landing, something like that.
Yeah, I forget what the initial schedule was on that.
Yeah, but like you mentioned, the lander wasn't ready.
Well, don't forget Apollo 1, too, the very first spacecraft, right? Yeah. That one, unfortunately, caught on fire, and 3 astronauts were killed in that accident.
Yep.
And that stopped all the Apollo program for like little over 2 years.
Yep.
And there were a lot of changes that had to be made. So it's nice to sit back, look at what you've done, and make sure you've done the safest thing possible where you have human cargo on board. And then proceed only when it's safe to proceed. And why I know we got to beat China to the moon. So there is a bit of a rush, but we shouldn't that shouldn't be the reason why we put people at more risk than what they already are.
Exactly.
That's the thing there. So we have to watch out for that. So that means 2028 would be a potential landing on the moon, either Artemis 4 or Artemis 5. And you know what happens and goes on in 2028?
Space Odyssey?
No, it's the last full year of the Trump administration.
Oh, okay.
This is where politics runs in because the appointment of the NASA administrator, for better or worse, is a political appointment.
Right.
And if you get appointed by a certain administration, you want to see things happen, if they can, while that administration is in power.
Yep.
And that's the push to get this done in 2028, because if not, then let's do it in 2029, because China won't get there till 2030.
Right.
but Trump will be out of office by a year or more, and whoever the next president is, regardless of the party, they'll get the glory for it.
Right.
You know,
It should not be happening
but
either.
that's the way it happens. I mean, when Apollo 11 landed on the moon, who was the president of the United States? Who got to call Neil Armstrong and Buzz Aldrin, from the Oval Office and talk to them while they're exploring the moon on the moon's surface?
Well, I'll give you a hint. He was not a crook.
Yeah, Richard Nixon. So, but obviously the Apollo program and in a sense, all of the human space program in the United States, really, you could argue, got started with John F. Kennedy.
Yeah.
Is the one that made the announcement, 61 was it or something?
Something like that, man.
To get to the moon before the end of the 60s and return somebody safely back to the Earth. So, yeah, so the administration that's in office at the time things happen, will get the credit. Just the natural thing that sort of happens. So that's the push. But, of course, safety is an issue. I'm not saying NASA's going to compromise the safety of the astronauts to get there in 2028.
But there is going to be a push.
That's a push, right?
Yeah.
And in fact, there's always been a push. It's just how you manage that pressure. Don't let it override you.
Agreed.
And we've seen disastrous things that happen because of people not controlling that pressure.
Yeah.
For example, the Challenger explosion, which we talked about back in January.
Yep.
Right? That was scheduled pressure that pushed and pushed and pushed to launch the shuttle as many times as you could in the given year. And it was too much.
Yep.
Anyways, NASA, and right now with the Artemis project, they can't do it. They can't launch Artemis 5 by the end of 2028. You know why?
Why?
Because it takes almost over 3 years to launch each of these SLS. The last one will be roughly 3 years ago that was launched, right?
Right.
So it's taking the crew, the ground crew, right? The engineers, the people that work on this stuff. The number of people they have employed presently, the civil service, it takes them about 3 years to turn it around and launch. And in those 3 years, there's a lot of memory that gets lost. That's one of the complaints that the NASA administrator had last week and voiced. And so he said to overcome that, we need to hire a lot more people. So there are going to be now jobs available at the Kennedy Space Center where you can work on the SLS and be part of the Artemis project to help speed up so that they can launch maybe every 6 months now instead of every 3 or 3.5 years. Yeah. That's the idea.
Okay.
So we're going to expand the employment.
So they've got an Elvis somewhere in the administration, is what you're telling me.
Well, here's the thing. How long does that last? Because, when budget cuts come along, what's one of the things...
science is one of the first things cut.
Well, I was saying civil servant jobs usually go out the door. So, but that's the only way that you can make the schedule. If you're going to launch, if you have a duty cycle of launching them twice a year, you got to have more people employed. It won't work otherwise. So that's the difference here.
Yep.
And that way, when you're used to launching, right, you're launching instead of every 3.5 years, you're launching every 6 months. You remember what happened before, and you can avoid those issues and try to get around them rather than forgetting. And it's not just forgetting, right? In the course of 3.5 years, how many engineers who work on the rocket actually left?
Yep.
Retired
or found better jobs.
Yeah, maybe they went to work with other companies like SpaceX or Blue Origin and all this kind of stuff. And then that information doesn't get transferred to the next
They have to
person that comes along.
refigure it out.
Yeah, well, that's the hard job, right? That's what slows everything down. Anyways, we knew the Artemis program didn't seem to going to be successful. We talked about that extensively last week, and I'm glad to see changes are being made.
Yes.
So anyways.
Hopefully it'll pick things up.
Hopefully it will. Okay, the next thing is something up your alley, Robert.
Yeah, kind of, anyway.
This is an interesting study. It's one of the, so you know what the supercontinent Pangea is all about?
I do.
Now, do you want to describe to people maybe you forget what this is?
Okay. Number one, I'm going to start off with saying that the continents of the Earth have at various points throughout history have come together into one massive supercontinent. Pangea is one of those supercontinent periods.
So that's the last one, right?
I think that's the last one.
Yes, that's the latest one. And that broke apart roughly, if I've heard, about 200 million years ago.
That sounds about right.
And so these continents have been splitting apart, plate tectonics, continental drift, have been splitting apart for the last 200 million years. And we have the technology easily, we've had it for many years now, that you can measure the increase in distance from North America to Europe and the decreasing distance from North America to like China, to Asia. because of the motion or the movement of the continents.
Movement of the continents. And this is measurable. I mean, this is not speculation anymore. This is through GPS technologies and other technologies. You can measure it. On average, it's about 3 centimeters per year of drift. So it's about the speed your fingernails grow.
Right. But still, over millions and millions and millions of years, it becomes very significant. It all adds up.
A few thousand years, and it's significant. And also keep in mind, this isn't like your fingernails where it's a smooth growth, okay? Like the San Andreas Fault, which is one of the fault lines at the boundary of these plates, demonstrates. It's an occasional pressure builds up and builds up and builds up and builds up, and then suddenly it just shifts, okay? So it's not a steady flow like your fingernail growth. So we use fingernail growth as an example, but it's actually an intermittent, spotty pattern of movement all along these front plate boundaries.
Yeah, so we got a question here. Did the Pangea shift bring worldwide volcanism that led to basalt events like the Deccan Traps in India?
It certainly did not help with that. And splitting of continents is often correlated, associated, that's the word, associated with an increase in volcanism. Because like the the Rift Valley in Africa
Right.
is where we actually have the African plate potentially splitting and spreading apart. It is a spreading center currently. Will it split the continent? We don't know yet.
So if you go to that location and look down, you know, people wonder, are you looking like down into the abyss? I mean,
no. It's like San Andreas Fault, okay? You walk into the San Andreas and you just see a valley. But every now and then it slips there and the crust moves, okay? So there is no pit or hole down into the earth at that point. It's just, it opens up a little bit. It spreads a little bit.
so how's all this related to like the Ring of Fire that we always hear about?
The Ring of Fire is another matter entirely. That's where you've got subduction zones because continental crust is lighter. It's made out of granite. It's much lighter than the basalt rock of the oceanic crust. Well, what happens when you collide a lighter material with a denser? The denser sinks, okay? So the Ring of Fire is where you have a bunch of subduction zones where that oceanic crust is being pushed underneath the continental crust. But that oceanic crust is filled with water and fluids and salts and things like this that reduce the melting temperature of the rock. Because as you increase pressure, you increase the melting temperature, right? So it's descending as rock, and if it were stayed rock, it would stay solid. The mantle is solid, folks. It is not a fluid. It is not liquid. Well, it is a fluid. It's not liquid, though. So what's going on at the Ring of Fire is it's subducting. Because of all that extra water and fluid, it melts in that gap between the continental and the oceanic crust, and that melt percolates up and explodes as volcanoes back behind the subduction zone. And so that's why it's a nice ring of fire around the Pacific Basin.
Well, how many plates are there altogether?
Oh, good Lord.
Like 20-some or something like that? Okay.
Because there's a lot of them you never heard of.
And
There's the major continents, but then there's like the Juan de Fuca, the Nazca, and a few others.
Are some of them like really difficult to detect? They're only like recent discoveries in the last couple decades?
You got it.
So why would they be difficult to detect? The fault lines are not as prominent as other ones?
Well, in like the case of the Juan de Fuca, it actually could be viewed as the old Pacific Basin plate. And what's happened is the new Pacific Basin plate, the new Pacific plate, has ridden up over it on one side. The North American plate is rising up over it on the other. And so it's just off of the coast of Oregon, but it's almost entirely gone now.
So are we talking about like plates that existed more than 200 million years in the past before the last supercontinent then?
You got it. We have seismic evidence that shows that there are actually plates that have been fully subducted. And in a lot of cases, they're laying at that core mantle boundary. They've subducted all the way down to the boundary between the core and the mantle. So, and we can see this because the rock has different density, so it affects the wave speed of the seismic waves. And so we can see this. from the reflection and refraction of the seismic waves.
So it's like you're seeing like brownies in your Blizzard from Dairy Queen, the chunks of
Yes,
like it's
it's
set.
very similar, except instead of opening up the lid and looking at it,
It's underneath.
I'm taking one of those ultrasound things that your doctors use and rubbing
Yeah.
along the side to see it that way, indirectly.
Wow.
So that's what I like to try to tell people,
Is
because seismic waves are just sound waves.
Yeah.
Okay, so it is our seismic measuring and metering is strictly sonograms on the Earth.
Now, is there a relationship between the depth of these remnants, if I can call it that, and how old they are, in the sense that the further down they are, the older they could possibly be, because they had more time to go downwards and descend?
Yes, but no. And the yes is that obviously the more time it has, the further it's sunk. But the other deal is there's a difference in the water content, which affects then the density, and then there's the density, which is affected by the chemical makeup of the rock. And so denser things, of course, fall faster through the fluid. And so how can the mantle be solid, by the way, but still fluid? Think of the mantle as a giant sand pile. Okay? You go out to an active sand dune region, you're going to see over the course of years the sand dunes move. That's what's happening with the mantle.
Right.
It's a big sand pile underneath our feet, or in a ball, and it's percolating because the grains are slipping and sliding against each other.
Now, this study that was recently published, as you see here on the slide, this getting to the reason behind how did the supercontinent break up 200 million years ago. And I guess it's not known for sure.
It is not known for, we have not seen it happen.
Yeah.
We are seeing it potentially happen. We have seen evidence of where it almost happened, like the Great Lakes. All but the two shallow ones, Ontario and Erie, were formed by a rift valley that didn't split the North American continent. But it tried to.
Interesting. And so the idea here is they're looking at different models or simulations, if you want to think of that terms, where in one case they thought that you'd need a warm mantle to initiate the breakup of the supercontinent. And this study is saying that's not necessarily could be the case, right? There's other ways of doing it.
And I would say not a surprising result. We've kind of known that. The Rift Valley, the mantle is no longer comparative to Pangea's time. The mantle is significantly cooler. I mean, we're losing about 100 watts per 100 watts of power through the crust from the internal heating of the Earth. So the mantle is measurably cooler than what it would have been 200 million years ago. And yet we still have the Rift Valley. In fact, this red line that passes by Congo Craton there in Africa,
Right.
that's pretty much the path of the Rift Valley. Okay? So
That almost looks like it was part of Madagascar or something in the past.
Madagascar was a part of it. Madagascar is a rift valley that opened up.
Interesting.
It didn't create a new plate or a new continent, but Madagascar was once in contact with Africa, and it split apart.
So it's moving its own independent way in that sense, right?
You got it. And this is another way we actually subtly know that the Earth is a sphere, because these things are not spreading away from each other like you would expect for plane geometry. They are actually twisting. They're torquing. So the top part of the Pacific plate is actually moving away from us in a different direction than California's part of the Pacific plate.
And that's why we know, like, around here where it was tropical millions of years ago,
And there's things like that.
because we were closer to the equator than what we are today.
Right.
Because of that migration. So it's not just strictly east-west type of motion.
You got it. Or north-south. It is a twist, a turn. There is a torque involved.
Interesting. Now, I know if you go to the next slide, Robert, so there's some different, the modeling itself that they're looking at. And you could probably say more about this kind of stuff.
I'm going to answer exploring the Ka with Ra for a little bit here, because that brings up a good point. The sun being the biggest energizer on the Earth. But you've also got to remember, the sun does not have any impact on us. Seriously, it really doesn't, outside of holding us in orbit and the insolation, the amount of energy we receive through photons. Okay? The solar wind is not enough of an impact. Our magnetic field blocks it. It is not enough of an impact to put a twist on us. The sun's magnetic field is not strong enough to put a twist to start flopping the core around to improve energy output that way and increase volcanism. And the mantle is not magnetic. It is an insulator. It is non-magnetic. So there's no torque that can be added there. So no, an extreme solar event would not have any effect on the tectonic, volcanic, or any other thing. It would compress our magnetic sphere a little bit, our magnetosphere. It would do things like that. But essentially, we're getting 1,000 watts per square meter insulation from the sun, so it heats up things nicely, but that's the atmosphere.
Now, if we go way back in time, billions of years.
Right. Now, then there's another matter entirely.
Because that's kind of related to the second part where he brought up about comets.
Yeah.
So if you're back in the era of the heavy bombardment time.
Oh, okay. I missed that part. Sorry about that.
There's a second.
Yeah. Now, the bombardment would have caused volcanism and things like that. In fact, there's no doubt that after the Chicxulub impact 65 million years ago, the Earth certainly rang like a bell. Rang like a big hammer struck the Liberty Bell. It almost certainly had more volcanism and things like that going on.
Right.
So, yeah.
So if you go back billions and billions of years, what started the whole plate tectonics, the drifting of the continents to begin with?
Go win your Nobel Prize.
Yeah, so nobody knows.
Nobody knows. Why didn't it start on Mars
Or Venus.
or Venus? We don't know.
Because Venus is essentially the same mass and size of the Earth.
Yep.
As far as we can tell, there are no plate tectonics like we see here on Earth, right, with continental drift.
Now, I do have my hypothesis, and I'm not alone.
It was related to water?
It's related to water. Because, like I was saying earlier, water lubricates the rock, makes it melt a little easier, and you can get some better pull down from the subducting crust, which rips it apart, which makes the mantle come up, and you get a mid-ocean ridge, and you start some tectonic activity going.
And what's the main source of water early on? The arrival of?
Asteroids and comets.
Yeah, so there's a direct connection there for sure.
Absolutely.
Interesting.
But seriously, this is one of those points where you can go out there and win a Nobel Prize. Because if you can figure that part of the puzzle out, you will have made a career.
But the problem is, it'd be a lot easier if there were remnants left over that you can analyze from that area, right?
There's a big part of the problem.
And so you're trying to find elusive evidence. Mm-hmm. That's extremely difficult to get a hold of.
We talk. How do we know the rocks on the Earth are to 4.3 billion years? Because we found what are called zircons.
Yeah.
Zircons are neat because they don't weather readily, so they don't erode. Okay, they do erode, but it takes a while. But they also have very slow diffusion rates for uranium, lead, and things like that through them. So whatever was locked into them is locked into them. Okay? But these samples we're talking about that they've dated these zircon crystals from, they're the size of large grains of sand.
Now, these material, you find them predominantly in places like Greenland, right?
Greenland, can I go back a slide?
Yeah, sure.
You see this word craton, C-R-A-T-O-N?
Oh, yes. Yeah.
Those are centers of old continental crust. That is the oldest continental crust.
When you say old, what do you mean? How many years?
We're talking at least, I think it's 3.5 billion years.
Wow.
Billion with a B. Wow. Okay? So all of these places where it says craton, those are at least 3.5 billion years old. That's where these old zircons are coming from. And if you notice, from the color, you've got one over here at the very edge of Australia, you can see. And that's where the oldest are coming from. It's this craton in Australia, the one up here in Greenland, the Canadian Shield, if you've heard of it.
Oh, yeah.
All that's cratons.
So Greenland's not even on this map.
No. And most of Australia is not. So a lot of the oldest crust is not on this map.
Now, is there one place that's the oldest of all?
Yeah, that's the Australian craton.
Okay.
That's what I was saying. And Greenland's got some pretty old rocks too.
So are you making a case why we should take over? No, just kidding.
No.
Now, getting back to this slide. So this is trying to understand more about how the supercontinent 200 million years ago broke out Pangea, right? And so
this is what I was studying in the little bit of time I had between when you handed me the slides.
Yeah.
And I went through them and was like, oh, I'll need to study up. And so I tried to find out, and I don't really know their argument. So I can make some guesses, and basically it looks like it has to do with that whole subduction thing I was talking about, except a lot of the molten material got pushed up onto the I think the word is abducting, the rising plate, and the lava and magma got pushed up and into it is what it looks like.
And how would you even know that that was one mechanism was dominant over the other?
Chemical composition. Okay? If it's deep ocean crust, it cooled very quickly. It's going to form igneous rocks called basalts. Okay? Basalts have a lot of iron-bearing, or they can have a lot of iron-bearing material. They're called mafic or ultramafic then. These hydrate very readily. And so you get hydrous chemistry going on. So continental crust, on the other hand, are younger, not ferric, I think that's the word, crust is more like granite and diorite, andesite, rocks like that. They're a lot more open crystal structure. They were under less pressure. They cooled a little more slowly, and you can push more into them. So a lot of this is done by looking at the chemistry and our knowledge of going in using high pressure presses and putting in the right combination of powders, pressing them, heating them up, and that's how that mineral forms.
Now, is there preferred areas where you would see these minerals, like along the edges of the plates?
You got it.
Okay.
You got it. And going back to that previous slide, this is what it's kind of showing by all the pretty blue colors and green colors. If you notice this bar up here on the upper right, that's the number of years. So the colors of that crust down here in the ocean is telling you how old that crust is.
Right.
From 0 million years ago for the deepest purples to 200 million for that brownish red.
So the Appalachian is really old.
Yep.
From this map.
You got it. And so a lot of this stuff is, again, it's from the chemistry, it's from the crystal structures, it's from the nature of the rock. This problem is when you get out here to 200 million year old rock, you are in a lot of cases, I'm sitting here swirling the cursor around like y'all can see it, but when you get to these older rocks, you've had enough time for chemical weathering and chemical changes due to mixing with the water and everything have happened. Pressure changes, temperature changes have happened, which change the structure and the chemistry of the rock. And so by the time you get to 200 million year old rock, you're actually dealing with a much different rock, usually actually now a metamorphic rock as opposed to an igneous.
Now, let's go into the future, millions and millions of years. So North America and South America will move towards Asia, and eventually they will collide.
You got it.
So then how does that, and then we'll form a supercontinent again.
We'll form a supercontinent again.
But does that break up then in the future? And how do things move? Do they move now all of a sudden the reverse course and go the other way?
They may. Probably not. Probably they'll grind against each other and away from each other. The stronger will break the weaker. Bottom line, we can see it going on with India ramming up into Asia and creating Mount Everest and the Tibetan highlands.
Can I think about it in a very simple toy model way, like a conveyor belt, and part of the belt is underground?
You got it. Yeah, that's actually a very good way of looking at it.
But how far deep is that bottom belt in the conveyor belt scenario?
From as near as we can tell, it can extend all the way down to the core mantle boundary.
Wow.
It does not necessarily. Okay, we have for many, 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 many years thought that the mantle in the interior of Earth was homogeneous, made of the same stuff.
Right.
This is proving with our LLVR zones and things like that we've talked about on the show, our large something velocity provinces. We're finding that the mantle is not as homogeneous as we thought. And that means it's not well mixed, and there may be differences in chemistry and thermal gradients and pressure gradients and things like that going on.
Now, we've talked on this podcast in the past about, and this is related to what you just mentioned, about evidence for the planetary Mars-sized object that hit the Earth in the past that ultimately led to the formation of our moon.
Mm-hmm.
That there might be remains of that deep inside of the Earth.
Yes. And that's been suggested.
Now, would that be a way to trigger ultimately plate tectonics?
Sure.
Which would explain why Venus doesn't have it, because it doesn't have a
It
moon.
didn't have that super impact.
Yeah.
You got it. And I will tell you this. There is no evidence for the core of Theia, or whatever you want to call that large impactor,
Right.
still being a separate entity. Okay? It's been estimated that if you took all the iron on the crust, put it into one ball, it would be just a few hundred years and it'd be in the core. Solid metal sinks through rock very easily, incredibly easily. So we're not seeing evidence of a second core to Earth. What we are seeing is some of its mantle material may not be mixed in with Earth's mantle material, even after 4 billion years.
Right.
So there's a lot to learn, folks.
Yeah, it certainly looks
There's
like that.
A lot we're trying to figure out.
Yeah, for sure.
All right, shall we move on to the next one?
Yeah, the next one, I mean, it's related because you wonder what impact, no pun intended, that the plate tectonics and all of that have on the formation of life to begin with.
Right.
For example, I mean, is there any idea how long plate tectonics been going on? Been going on for? We're talking 3.5 billion years.
I think that's the current estimate. Is about.
I mean,
3.5
that's
billion
back
years.
like when the oldest life forms on Earth, stromatolites in Australia, for example,
And so, are those two processes linked?
related somehow.
These are great questions. These are ones we're trying to figure out.
Yeah. So this slide actually is something interesting. It's if you like, a team of scientists that published this paper recently in Science. And it's based on the fact that people are experimenting now with what they call mirror life.
And let's hope they stop.
And what's mirror life? When you look in a mirror, then your right hand is now your left hand and vice versa.
Mm-hmm.
And so you just get that, what we call parity exchange in physics. And in this case, what we mean is the handedness of things. So if you look at DNA and RNA, and we talked about these things like with Becky and others, that they are what we call right-handed.
Yep.
But-
And the proper technical term is chirality.
Chirality. And the other way you could have life is to be left-handed.
Mm-hmm.
And it turns out that when you develop life artificially, or you try to do it in a laboratory, and make it left-handed instead of right-handed, that could, if it somehow escape, and of course, we would never develop anything in a laboratory of biological nature that would ever escape COVID. You know, nothing would ever happen, right? So we don't have to worry about this stuff. Well, of course we do. And you know, it's been
when
what?
will Elvis get here?
You know, it's when you think about it, it's almost, so today's the 3rd of March. In 10 days from today, it'll be exactly 6 years since we got the notification that we were closed down as a university because of COVID infection in 2020.
Yeah.
So we're almost 6 years there to the day. So it's been 6 years. Where did COVID come from? I'm still waiting for the answer to that question.
Well,
And
it's
you-
a common virus.
Well, you hear
It's
it.
a
Yes,
common
it's the
virus type, I should
coronavirus,
say.
so it's
It's a
related to the
coronavirus.
cold virus. I know, but where did COVID-19 virus come from? If you want to make me more specific here.
Yeah.
And we heard two possibilities. It was developed in a lab in China and released somehow.
Or it mutated spontaneously.
Or it came from one of those wet markets or something,
Yeah,
right?
it mutated spontaneously and went through there. Yeah.
But and I think there is so much politics involved in that question now.
I don't think we'll ever know. the answer.
We'll never know, because it seems like people are hiding it,
Yep.
or they burn the records, and we'll never know what. But it's related to this story.
It kind of is, yes.
Because if we ever develop something in a laboratory, and this is what these scientists are saying, that's left-handed, our immune system, all of the things that we have in our body currently to protect us from various diseases and viruses and bacteria and so on, that have a fighting chance of killing it before it does major harm to us, would be totally useless if it's left-handed.
Yep. Because it won't recognize that it's even there.
So it'll go right through our immune. It sounds like it's like a developing of a stout aircraft, stealth, right? Technology.
I will put it this way. Think of it like a key. Your immune system and all its enzymes and RNA and messenger RNA and all these things operate on that right-handed chirality, which means that they key into each other. Okay? If it doesn't key onto it, it doesn't key onto it. Well, what's that got to do with a key? Well, if you notice on your house key, there's one side that's got like this one thin groove on it, and the teeth are shaved flat on that side, and the other side has a wider groove in it. Okay? Now, flip the sides with those grooves and that shaving of the teeth. Is it going to work in your door? Your door probably won't even go into your door lock.
Yeah.
Okay? And that is the problem. Your immune system is keyed to right-handed life to look for that key sequence to lock onto it and destroy it.
Now, let's say there's enough sensibility with scientists in this world and others that control the funding, i.e. politicians, that we realize the risk that this could bring if something got released. You know, it's the ultimate horror story, right?
Right.
That a virus gets released, the Andromeda strain.
The Andromeda strain.
Right, it gets released and it's left-handed instead of right-handed. We have no protection and can't do anything about it until we develop something to kill left-handed stuff, life.
And then
like
that
virus.
stuff will kill us too. So.
Yeah. But you could, you know, we talk about astronomy in this podcast, obviously. How do we know that if we don't go somewhere, okay, where there's life, and that life on this exoplanet is left-handed and not right-handed. So that would be potentially deadly to us.
It may be completely benign, though. Don't forget that. It wouldn't really notice us any more than we'd notice it.
What happened to the First Nation people when Europeans came over to...
And there's the real nub of the problem. It might not be a problem. The French Canadians got along fairly well with them. They traded with them. They partnered with them in a lot of cases. But then you had other groups that came over and said, nope, this is our land now.
Smallpox.
Right. So this left-handed life may not even notice us any more than we notice it. But it may.
Well, I was going to say, how do we know that it's even dangerous to us? Are we even guaranteed of that?
We really don't.
So then,
but is it worth the risk?
So should we develop left-handed life like bacteria in a laboratory, and have it merge with right-handed life like a mouse, because we always seem to pick on mice, and see what it does? Is that going to be the big experiment?
I would be willing to fund that experiment on several caveats. One of the biggest being it's held deep underground with lots of airlocks and
or on a
ventilation
space
exchanges,
station.
Or on a space station, and there is a nuke attached to it.
Yeah.
So that if it starts to even look like it's getting out,
well, you can do all this remotely, right?
Right.
You don't need human beings to interact with it directly, right? We have the robots, in other words.
I'm like,
just a poor mouse.
I don't want this anywhere near where it can get out and into the G-pop. Because if we're right about how dangerous it is, we're screwed. If we're wrong, we've learned something interesting what to look for out there in space. Because energetically, there is no reason to favor right-handed over left-handed molecules. There's absolutely no reason.
Very scary when you think about it. Now, the last story that I wanted to talk about today is actually this finding related to the moon. And it's the information that actually came from further analysis of rocks that we gathered back in the Apollo program. So at the beginning, we talked about the Artemis project. And one of the smart things that we did in the Apollo program days is that we didn't analyze everything we brought back.
Yep.
We
and
took
still in the process.
Yeah, we took a large. In fact, a majority
is still unanalyzed.
Of the rocks and soil is locked away, hopefully in a place where we don't disturb it or no earthly way of affecting it.
Once upon a time, I applied for a curator position over that.
The Lunar Receiving Laboratory.
Yep. I did.
Nice.
I didn't hear anything back from them, but I did apply for a job.
Yeah. I guess you should go there and throw a rock at them from not replying.
Yeah. I don't like
No,
getting
don't do that.
ghosted,
Don't
but
do
it was
that.
still funny.
Anyways, so yeah, so you never know what you find, and the idea behind that was, well, this is the technology we have now in the early 70s. You think of 72 when Apollo 17 was done. Who knows what type of technology we'll have in the year 2000?
And that's
So let's save a lot of this material for
Yep.
future scientists to analyze. So part of that is what this study was about. In fact, they link essentially the magnetic field strength on the moon, which we thought the moon did not have a magnetic field, it's very weak, to actually by analyzing the rocks, and these are linked to the ones that we landed in Apollo course, which have high titanium content.
right.
That you actually, from that analysis, you can actually determine that back in the early part of the moon's history, there were times where the magnetic field was even stronger than the magnetic field here on Earth.
Yep.
And there were other times where it was weaker. So it went through this episodic sort of changing in strength of the magnetic field.
And this is a guess. This isn't even a hypothesis. But if I had to guess, it has to do with the iron melting out of the rock that formed the moon and drifting to its core. When it moved quickly, it had a strong magnetic field because magnetism is produced by moving charge. When it did so out, that's what this figure.
Yeah, that's why I went to... There you go, Robert. Keep talking.
So, yeah, when the metal moves slowly, it's not a fast-moving charge anymore, so it produces a very weak field. And the neat thing is like I mentioned, those basaltic rocks, which are magmatic in nature, they're ferric. They contain iron and titanium and will accept a magnetic field. And when they harden, then that magnetic field is locked in. And so you're left with this very faint but measurable magnetic field locked into the mafic rocks.
I mean, it's not unlike the reason that we can tell that we have pole flips here on the Earth.
Bingo. It's the exact same process.
Yeah. Interesting.
So, yeah, I was rattling off of this. Then we went to the next slide, and I
There
stopped
it
look
is.
at it. I'm like, oh, wait, there it is.
Now, did you notice I'm making you talk more today because you won't be here next podcast?
I won't be next podcast. I may be with you guys because I won't be doing anything
okay.
Tuesday.
We'll send
so
in
I
your
may-
comments and your questions.
I may send in my own comments.
That's a good idea. Now, if you're interested in geology, if you're interested in the continental drift and why the continents broke up 200 million years ago and what happened and what's going to happen in the future, all of that, what should you do, Robert?
You should come to higher learning. You should look at places like the University of North Dakota. You should just improve your knowledge. If you want to talk about this, draw those figures, make it STEAM, come in and join our art program, just further. And even if you're not interested in doing this professionally, you can still check out some online classes. You can still continue learning.
And please don't forget, our next podcast will be a week from now, so on March the 10th, where I will be solo.
Yep.
And if we don't go on live, you'll know I'm having problems, but hopefully I've already practiced a few times, and it seems to work.
I'll make sure he has my phone number.
I'm going without I'm going to be producer less, you see? So hopefully I can...
We'll hopefully get him on air, and we'll get the podcast out.
We can entertain you now. Now, at the end of all our podcasts, we always leave you with a quote. And today I decided to pick a quote from an article that was published in Scientific American magazine back in December of 2014. And this was a quote from Gene Shoemaker. So Shoemaker, unfortunately, passed away in 1997. There was an article about him back in 2014, which is where I got the quote from. And Shoemaker is well known because he was one of the main geologists that worked with the Apollo astronauts to train them what to do when you went to the moon. In fact, if we would have continued the Apollo program, chances were that he was eventually going to go up.
Oh, I did not know that.
Yeah. And in
I
fact,
also know he was a great comet hunter along with his
that's right. And
partner,
Shoemaker
Levy.
Levy-9 is famous for that. And in fact, Gene Shoemaker was killed in July of 97 when he was in Australia and got killed in a car accident. And he was down there because of geology, doing different trips, field
There we
trips
go.
and stuff.
And there's a reason they go to Greenland and Australia.
Yeah, exactly. So here's the quote. We expect that the study of lunar geology will help to answer some long-standing questions about the early evolution of the Earth. The moon and the Earth are essentially a two-planet system, and the two bodies are probably closely related in origin. In this connection, the moon is of special interest because its surface has not been subjected to the erosion of running water that has helped to shape the Earth's surface. So if you want a reason to go back to the moon,
There you go.
there you
It
are.
also has no plate tectonics. The volcanism is old. So many reasons.
No wind.
No wind. So many reasons, folks.
Anyways,
Anyway,
if you like this
great quote.
podcast, please give us a thumbs up. Subscribe if you haven't subscribed. And hopefully, we will see you
Next
next week.
have a good one, folks.